How many people do you usually show up?
Here we go. Welcome, everybody. I might be pausing here as I'm letting more people in and whatnot, but just wanted to welcome everybody to the Robert Ferguson Observatory Speaker Series. My name is Sreevani Jarugula, for those of you who don't already know me, and I'm the Executive Director of the Observatory, and we're so thrilled and honored to have Sreevani Jarugula here with us today, and I'll present her in a moment or introduce her. But before we start, again, just wanted to remind everyone to please keep yourselves muted to minimize that background noise. And feel free to go ahead and put questions in the chat as Sreevani goes through her presentation, and we'll either address some of those questions, if there's a pause in the moment when she's doing her presentation, or we'll wait until the end. So we'll kind of play that a little bit by ear. But if you don't mind putting them in the chat, and then, at the end, we might be able to also unmute ourselves as well if we have time for that. So for those of you who don't know about the observatory, we are run by the Valley of the Moon Observatory Association, which is a 501(c)(3) nonprofit comprised of volunteer, amateur, and professional astronomers. RFO has fulfilled its mission of offering educational programs about science and astronomy for students, the public, and in support of educators for about 25 years. We're truly a public observatory. We are almost all volunteer run and typically serve about 9,000 visitors annually. And we are located in beautiful Northern California in Sugarloaf Ridge State Park. And the observatory houses a 40-inch reflector telescope, the largest telescope in Northern California that's accessible to the public, a robotic 20-inch research-grade CCD telescope, and an 8-inch, 2-meter long refractor telescope. The observatory has a robust volunteer program. So if anybody is interested in volunteering and getting involved, you can get a volunteer application on rfo.org, our website. And we actually have a new volunteer training starting the end of this month. So it's a good time if you're interested. We also have a membership program, which is another great way to get involved in the observatory and get some cool member benefits along with that. Obviously, the information for that is also on our website. And then lastly, I just want to mention that we have kept the presentations in our speaker series free to the public to align with our mission of offering educational-based astronomy programs to our community. That being said, if anyone is so inspired to donate to the Robert Ferguson Observatory to ensure that we can continue fulfilling that mission, then you can also do that through our website, rfo.org. So now for the part you all came for, I wanted to introduce Sreevani Jarugula, is a postdoctoral research associate at Fermi National Accelerator Laboratory, which is located just outside of Chicago in Illinois. And so she's zooming in from Illinois. And so kudos to her for being up she's 2 hours ahead of us. So really appreciate her still being willing to do this time. She works on developing machine learning algorithms to study cosmology using strongly lensed galaxies. Prior to this, she worked with the South Pole Telescope submillimeter Galaxies collaboration, where she studied early star-forming lensed galaxies through molecular observations. Dr. Jarugula received her PhD in 2022, again, congratulations, from University of Illinois, Urbana-Champaign. And so without further ado, I will pass it on to you.
Thank you, Stephanie. Let me share my screen. And thank everyone for being here and just giving me this opportunity to present. It's my first time presenting at Robert Ferguson Observatory. Really exciting to be here. My name is Sreevani Jarugula. I am currently a postdoc at Fermi National Laboratory. And as Stephanie mentioned, I recently got my PhD in December last year, where I worked on the special sources called dusty star-forming galaxies, which are gravitationally lensed and at really high redshift. And by high redshift, I mean really early in the universe. So here I'm going to talk about this phenomenon called gravitational lensing, how it's going to help us study this early universe at a really high resolution, and what telescopes we use for these studies. This is a beautiful picture of a galaxy cluster. And if you squint closely, you can see that the light from some of these sources looks distorted. And I can highlight some of these sources here. So these 4 blobs that you see are actually coming from one source, which is behind this gravitational cluster, much farther than this galaxy cluster. And this light from this one source is being distorted and producing these multiple images that you see here. And this is from a lensed quasar. And if you see more carefully, you can see that these 3 images highlighted here are also coming from one source. It's coming from a galaxy behind this galaxy cluster. And that light is also being distorted and producing this arc kind of structures. So here's another example of a galaxy cluster. And you can also see that the light from some of these galaxies is being distorted into these arc-shaped structures. And if you squint more closely, you can see that the universe is smiling at us. So what exactly is this phenomenon of gravitational lensing? It's actually a prediction of the general theory of relativity proposed by Albert Einstein in around 1912. So according to the general theory of relativity, the gravity and space-time are connected. So if there is a massive structure closer to us, like a foreground galaxy or a galaxy cluster, the mass of this galaxy is bending the space-time around it, and that distorts the light coming from a source behind this foreground galaxy. Let's call it a background galaxy. So because the light is being distorted by this foreground galaxy, what you actually observe is a magnified version of this background source. And it is not just magnified, you can also observe this galaxy at a higher resolution, which helps us study this high redshift or early galaxies. So you can think of it as exactly like a magnifying glass. So this foreground massive galaxy is acting like a magnifying glass, and it's magnifying a fainter, farther away source behind it. So the arc structure you see depends on how massive the foreground galaxy is and how the orientation of the background source and the foreground galaxy is. So it depends on the distance between the observer, us, and the lens. It depends on the distance between the lens and the source. And it also depends on the distance between us and the source. So there is a orientation dependence on how these lensed galaxies will look like. Here's a nice demonstration of how gravitational lensing works. This is a nice video where they move a wine glass on an image of a galaxy and see how the light from this galaxy picture is being distorted as you move this wine glass. Yeah, can you see the video? Yeah. So as you see that as it moves closer into the center, you can see a full ring-like structure. And as the glass moves away from it, that ring sort of breaks off and you see only the arc kind of structure. So the orientation depends on where the lensing galaxy is. So you can think of that wine glass as a foreground galaxy. Let's look at this video again because I like it. I feel like this is a good way to demonstrate the bending of light. So you can see that full ring structure here, and then now you can see the arc structure as it moves away. Let's look at some history of gravitational lensing. Like I mentioned before, the curvature of space-time and how the massive structures bend space-time was already predicted in general theory of relativity in around 1912. But the first test of general theory of relativity was done in 1919 when during the solar eclipse. So what they did was they looked at the position of stars before the eclipse. And then during the eclipse, when the sun came in front of these stars, they looked at the position of these stars again. And because of the gravity of the sun, the light from the background stars was distorted and the position of these stars was shifted. And that's how they could test the general theory of relativity. And this was a big deal back then. And a lot of scientists followed up the theory and theory of gravitational lensing. And this, like I mentioned before, it was first proposed by Einstein in 1912. And you can see the notes on the right, all the equations of how the light bends because of this lensing phenomenon. But it was only published in 1936. Like if you read this publication in Science, Einstein says that sometime ago, R.W. Mandel, who was an amateur engineer, he paid Einstein a visit and asked him to publish the results of these calculations after almost like 2 decades, right? Which I made at his request. Clearly, Einstein didn't want to publish his results, but was asked to publish. One reason was because Albert Einstein and also all the other scientists who followed up this gravitational lensing thought that it was almost impossible to observe this phenomenon of gravitational lensing, where you can see these arcs or double lenses, double images, because having that perfect orientation of 2 stars to observe this phenomenon was thought to be almost impossible. Like the mass of the star has to be perfect. The orientation between the background star and the foreground stars has to be perfect to get that ring-shaped structure. And so they were a little skeptical on how this could be observed. But Zwicky, in I think 1970s, proposed that galaxies can be used as gravitational lenses, and a farther away galaxy light could be distorted, and then you could see this ring-shaped structures. And this was when the galaxies were first discovered. And once Zwicky proposed this, the first gravitational double image was discovered in 1979. So on the right, you can see this beautiful image detected in radio emission of a background galaxy being doubly imaged. You can't see the foreground galaxy here because this is a radio image and the foreground lens is not bright in radio. There's just the background source is bright in radio, and that's why you can see only the lensed background source here. Following that, in 1985, there was a first detection of this 4 quadruple images of a background source. This is called an Einstein cross. And in 1988, there was this first detection of a ring of the background source, and this is called an Einstein ring. Because Einstein came up with this theory of gravitational lensing, they started calling it the Einstein ring and Einstein cross. So what is the science that we can do with this gravitational lensing? And one really obvious thing we can think of is, yes, we can study these really faint galaxies which are really far away from us at really high resolution, because gravitational lensing is magnifying these sources and also increasing their resolution. Here I'm showing 3 images of a source. In the leftmost image, these are all simulations, by the way. So the leftmost image is a source observed with the Hubble Space Telescope. And you can see the resolution is not great. And in the center image is the same source observed with the James Webb Space Telescope near infrared camera. The resolution slightly improves, but still it's not great. But what if the same source was gravitationally lensed, and then you model this lensed image to reconstruct the original structure of the source? And that is how it looks like. So on the farther right is a galaxy which is gravitationally lensed and observed with James Webb Space Telescope. And you can see the incredible increase in the resolution. You can see all these stars within this galaxy. You can see all the dust and gas. So this is the power of what gravitational lensing can achieve in terms of increasing the resolution of these farther away early galaxies. And not just distant faint galaxies, but we can also study the matter content and distribution of this lensing galaxy itself, and also constrain the theory of expansion of universe using these gravitational lensing. So in the right, I'm showing you the contents of the universe. Most of the universe is made up of dark energy, about 70%, which is causing the expansion of the universe. And about 25% is matter that we don't see or we don't detect. We can't detect directly, is the dark matter, which is interacting with gravity. And this dark matter is responsible for structure formation in the universe. And only 5% is what we actually detect and is interacting with photons, like galaxies, planets, stars. So because gravitational lensing depends on how much mass is actually causing this lensing, you can, with models, you can constrain how much matter there actually is in addition to the visible matter. So you can, with proper modeling of gravitational lenses, you can say, okay, there is, you need this much dark matter in this galaxy cluster to cause this gravitational lensing. And because gravitational lensing also depends upon distances, with modeling, you can constrain the expansion rate of the universe and also constrain the cosmology that is causing the expansion of the universe. So all this is important science that can be done with gravitational lensing. Okay, so in this talk, I am gonna talk about these dusty star-forming galaxies, which are at high redshift and which are gravitationally lensed. And these dusty star-forming galaxies are bright in infrared. They are first, the galaxies that I'm going to talk about were discovered in the South Pole Telescope survey, which is actually a CMB experiment. And that's shown in the left image here. It's a CMB map that you see. And these show up as bright blobs in this map. And we followed up these sources with the Atacama Large Millimeter submillimeter array, ALMA, and also the recently launched James Webb Space Telescope in December 2021. So we had some really great observations coming in with James Webb Space Telescope as well. And you can see the incredible resolution images in the bottom with ALMA and James Webb. So I'm going to deconstruct all these technical terms in the talk, and I'll discuss what dusty star-forming galaxies are and what actually we observed with ALMA and James Webb in these galaxies. Just to start with the very big picture, here is the cosmic evolution of the universe. So our universe, as we all know, started with a Big Bang, followed by a period of inflation and expansion. At about 400,000 years, the first light that you see which we now detect as is cosmic microwave background radiation. So at this time, the first atoms, hydrogen and helium, were formed, and they quickly went to the lowest energy state, releasing photons. And those are the photons that we now detect in millimeter wavelengths as the CMB. This was followed by dark ages, where there were no new sources of light except the photons that were released by hydrogen and helium, and also sometimes the 21 centimeter line from the neutral hydrogen. But there were no new sources of light. And about 0.1 billion years ago, the first stars and galaxies started forming, and they started reionizing the universe around it. And that's called the epoch of reionization. Following that is all the structure formation that we now currently see around us as galaxies and galaxy clusters. In the bottom, I'm just showing some phases of galaxy evolution, wherein galaxies merge together, and then because of this merging, there is an intense star formation activity occurring in these galaxies, and then all the gas and dust is emitted out of these galaxies, and eventually that forms an elliptical dead galaxy. So it's really important to study these early galaxies to understand the conditions in the early universe and how these galaxies have been evolved to the present universe that we see around us. And it's really important to observe our universe not just at one wavelength, but at multiple wavelengths. So multi-wavelength observations is crucial to get the big picture, the entire picture of our galaxies. So here I'm showing a galaxy called the Whirlpool Galaxy at different wavelengths. Starting from the right, you have X-rays at, these are short wavelength, very energetic observation of hot gas, and then followed by ultraviolet radiation. So the young stars are bright in ultraviolet. So when you observe a galaxy in ultraviolet, you're actually seeing all of these young blue stars. And in optical, this light is coming from older stars. And also there is a lot of dust that you see here, which as these dark bands in this galaxy, which is obstructing this UV and optical emission. And then in infrared, you actually see that the dust is glowing in infrared. And it's also, you see more of this cooler gas in infrared wavelengths. In radio is also cold gas that you observe, such as carbon monoxide molecules. And we have so many observatories at observing our universe at multiple wavelengths. We have Chandra X-ray Observatory, which is a spaceborne observatory to get the X-ray observations. And invisible, we have the Hubble Space Telescope and also James Webb Space Telescope for the near to far infrared. And if you go to millimeter wavelengths, we have the Planck Observatory and the South Pole Telescope. And if you move further to millimeter and submillimeter, we have ALMA. In radio, we have the Very Large Array VLA and the Square Kilometer Array SKA, which is coming up. So I have done most of my work using the ALMA South Pole Telescope. And since last year, we've had observations with the James Webb Space Telescope. And as during my postdoc, I'm also working on the Vera Rubin Observatory, which I'll briefly talk about towards the end. It's an optical telescope, which is going to go online in 2024. This is going to be a survey telescope, again, going to revolutionize our understanding of the universe. Was there any question?
I don't think so. Yeah, sorry.
Okay. So I mentioned that that I am mainly interested in looking at these dusty star-forming galaxies, which are bright in infrared. So why do we even care about infrared emission? Why is it important to look at our universe in infrared wavelengths? One main reason is that the dust scatters the visible light, but is transparent to infrared radiation. So here's an image of what's called the pillar of light. It's a nebula. I think on the left is observed with HST, if I'm not wrong. So if you look at visible light, if you look at the optical wavelengths, you can see that the dust is obstructing most of the starlight in the left panel. But if you observe the same same object in near infrared, you can see that it's glowing really bright. You can see all of that starlight behind this dust, because in near infrared, the starlight just passes through all of this dust. And not just this, if you go to longer and longer wavelengths, the dust actually glows in longer wavelength. So what's happening is that the dust absorbs all of that ultraviolet radiation from the stars, and it gets heated up and it starts emitting in far infrared wavelengths, and it starts glowing in far infrared and submillimeter wavelengths. So this is the Milky Way observed at different wavelengths. In the bottom is the optical visible light, and you can see a dark patch in the center. And if you go to near infrared, you can see some stars start showing up here. And if you go to far infrared and submillimeter, the dust is actually glowing in far infrared and submillimeter. The dust is actually emitting in these wavelengths. So if you just observe our universe in optical, you're going to miss a lot of this light, because it's going to be obstructed by dust. Here is a simple plot on the energy content at different frequencies. CMB is cosmic microwave background radiation, where most of the energy cosmic background is coming from. And then CIB is the cosmic infrared background, and COB is cosmic optical background. So if you're only observing the universe in optical wavelengths, you're missing out almost 30% of the energy which is being emitted by this infrared sources like dust. So that's why it's very important to study the universe, not just in optical, but also in infrared, to get the entire energy budget. So what is dust? Dust is actually a carbon and silicate compounds. I think if I remember correctly, the size varies from about 0.1 micron to 1 millimeter. And so here is a dust structure at 1 micron. So it's a complex molecule with carbonates and silicates in it. So dust is mainly produced by stars at the end of their lifetime in the asymptotic giant branch called the AGB stars. And also when they blow up as supernovae, they release a lot of dust in addition to different elements into the interstellar medium. Dust is also very important because a lot of chemical reactions are occurring on the surface of dust, producing molecules in the interstellar medium, which I'll briefly talk about later. So I'm interested in dusty star-forming galaxy, and as the name suggests, these galaxies are dusty, and because they are dusty and star-forming, and there is a lot of star formation going on, they're bright in infrared because all this dust is absorbing the ultraviolet radiation from the stars and emitting in infrared. So in the plot here, this is again how much energy is being emitted at different wavelengths. And if your galaxy is free of dust, the dust free shown in blue, most of the light is coming from UV and optical light. But if you have dust in your galaxy, then some of this ultraviolet and visible light is absorbed and then emitted in far infrared. That's why you see a peak in far infrared wavelengths in case of dusty star-forming galaxies. Okay, so we've discovered about 81 dusty star-forming galaxies in the South Pole Telescope survey. South Pole Telescope is a single-dish CMB telescope at the South Pole. It mainly operates at 3 wavelengths at 1.42 and 3 millimeters. And it's covering a huge amount of sky. It's almost 2,500 square degree survey. And you can see how the survey map looks like. All the wave structure you see is the cosmic microwave background radiation. And if you zoom in, you can see that the dusty star-forming galaxies show up as bright blobs in this map, and the darker spots are galaxy clusters. So we followed up with these bright blobs with high-resolution telescopes to actually study what these galaxies are. So why were these galaxies found in a millimeter survey? One is that the infrared light from these dusty star-forming galaxies are being redshifted into millimeter wavelengths. And that's why we observe them in millimeter and submillimeter wavelengths. To remind all of you what a cosmological redshift is, as we know, our universe is expanding. So if a galaxy emits in shorter wavelength, because of this cosmic expansion, by the time the light reaches us, the wavelength has changed to longer wavelengths. So if the galaxy emits in infrared, by the time it reaches us, if it's really far away, by the time the light reaches us, it has redshifted into millimeter wavelengths, a longer wavelength. And there is also another phenomenon called the negative K correction, which is compensating for the decrease in the brightness as you move the galaxy farther and farther away. And that's what I'm showing in the plot here. It's slightly difficult even for me to wrap my head around this, how this works. So if you take a galaxy and move it farther and farther away from us, the light that we see from these galaxy grows dimmer. So if you see the energy distribution at different wavelengths, and the peak is far infrared. So black is a galaxy closer to us at redshift 0.01. And red is a galaxy which is at redshift 6. So it's much farther away from us. So if you take this galaxy and move it farther from us, the overall brightness of this galaxy decreases. But as you move it farther and farther away, the light is also being redshifted. So you're moving up the slope. So this phenomenon kind of compensates for the decrease in the overall brightness. So the brightness essentially doesn't change in these wavelengths, even if you move it farther and farther away. In addition to this, we have gravitational lensing, which is actually increasing the brightness. And all of this together has made it possible for these bright infrared sources to show up in our CMB maps. And we followed up with Atacama Large Millimeter submillimeter array. This is one of my favorite telescopes. I've used it throughout my PhD work. It's located in Chile. It's an interferometer. So there are 54 12-meter dishes and 12 7-meter dishes. So you can see some of these antenna here. So this is operating in millimeter and submillimeter wavelength. So it goes from 320 micron to 8.6 millimeters. And this is a very highly sensitive telescope. It can observe these galaxies at high spatial and spectral resolution. So we can study all the dust and gas content in these dusty star-forming galaxies with ALMA. And here are some beautiful images with ALMA. So the blue is actually optical images from HST. And you can see the foreground lens in optical images. And in red, you can see the Einstein rings from these high redshift background dusty galaxies with ALMA. So this is really high resolution images where all the rings are clearly seen and separated from the lens. And we also have recent observations with the James Webb Space Telescope. Here is an image of SPT 2147 -50. So the background is actually HST optical image. So you can see the lens here. And in green is the source observed with ALMA. And now let's look at how the source looks like with James Webb Space Telescope. That's how it looks like. So with James Webb, you can detect both the lens and the background source, and you can see the incredible resolution and brightness increase with James Webb Space Telescope. So these are some incredible images, and we are getting some really good science out of it. And I'll show a couple of more images later on with JWST. This is really an exciting time for dusty star-forming galaxies. Okay, so now we have gravitational lensing to help us look at these really far away galaxies. We have these incredible telescopes like ALMA and JWST. So what exactly are we looking for in these galaxies? One of the things that I'm interested in is the atomic and molecular observations from these dusty star-forming galaxies. And these molecular studies are very important to understand the properties of galaxies, such as the star formation rate, for example. It's one of the important observables of a galaxy. It's the number of stars that are being formed. And you can get the star formation rate directly by observing in ultraviolet radiation, because that's the light from young stars. So if you can observe UV emission directly from these young stars, you can say what the star formation rate is. Or in case of dusty star-forming galaxies, you can observe them in infrared radiation, where the dust is absorbing UV and emitting in infrared. So that also gives the star formation rate content of the galaxy. But you can also get the star formation rate from molecular observations like water, H-alpha, Paschen-α, doubly ionized carbon, and you can get the gas mass, which is how much gas there is in the galaxy, or the potential to form stars from molecular hydrogen. Carbon monoxide is an important molecule to get the gas mass. And also you can study if the galaxy has a black hole and there is an accretion disk, you can study this active galactic nuclei through observations of these polyaromatic hydrocarbons or highly ionized oxygen lines, highly ionized silicon lines. So all these ionic atomic molecular studies can give a lot of information about the galaxy. So here's the Milky Way observed with atomic hydrogen, 21 centimeter line in the left, and carbon monoxide in the right. So our universe is mainly made up of hydrogen and helium, and oxygen is the third most important element. And the hydrogen and helium were mainly formed from Big Bang. And most of these elements that you see in the periodic table are formed in stars, and they are released into the interstellar medium through supernovae, or there is also a lot of cosmic ray chemistry which goes on, and there are merging neutron stars, exploding white dwarfs. So I really like this periodic table, which shows how and where all of these elements are formed in the universe, but where the molecules formed. So all of those are elements, right? And this picture nicely summarizes what's going on in a galaxy, in the interstellar medium of a galaxy. So all that dust and gas condenses to form stars, and most of the molecules are formed in these really dense gas and dust clouds. So this is where star formation occurs, and most of the elements are formed in these stars. And as these massive stars explode as supernovae, they give off some cosmic rays. So there is some cosmic ray chemistry, which is giving rise to formation of, say, carbon monoxide molecules. But a lot of chemistry also occurs on the surface of grains. This is called grain surface chemistry, where water ices, carbon dioxide ices are formed. And all of this, again, goes back into the interstellar medium and into these clouds. So there is a lot of interaction going on between stars, dust, gas, in formation of molecules. My main focus was on water molecules. So as we've discussed before, the UV light from the stars is absorbed and re-emitted by dust. And this infrared light is actually exciting these water molecules to a higher state. And when these water molecules from this higher state come down to a lower state, they emit some photons or light. That's the light we observe to study water molecular distribution in the galaxies. And here's an image of a gravitationally lensed source. And this is actually water emission that I'm showing here from a galaxy at a redshift 3. Another cool galaxy that I worked on is SPT 031158. So this is a galaxy, one of the earliest galaxies in the universe at redshift 6.9, which is close to just 800 million years after Big Bang. So this is one of the first galaxies that was formed in the universe in the epoch of reionization. And we have detected several molecules from these galaxies. And I'm showing some of these here. We have detected water, as you can see in the blue line here. So this is actually two galaxies which are interacting with each other. And we've detected water from these galaxies. We've detected different carbon monoxide transitions. So CO6 to 5, CO7 to 6. These are this carbon monoxide is mainly tracing star forming regions in these galaxies. And CO10 to 9 is a slightly highly excited state of carbon monoxide. It's tracing slightly hotter gas in the galaxies. And we've also had one of the earliest detections of Paschen-α from this SPT 041847. So Paschen-α and H-α are the hydrogen atom transitions. And this is one of the earliest detections of Paschen-α with James Webb Space Telescopes, which is really exciting. And we also detected some polyaromatic hydrocarbon emission from these galaxies. So all of this information is crucial to estimate the basic properties such as star forming rate, and to calibrate the star formation rate against other known calibrators like far infrared emission, for example. So Vera Rubin Observatory is, like I mentioned, it's going to revolutionize astrophysics and what we know about the universe. It's an optical telescope in Chile, and it's going to go online in 2024. So currently I am working on Vera Rubin Observatory simulations, and also what kind of science we can do with Vera Rubin Observatory. It would be really interesting if someone can talk about this in these speaker series. So this is a survey telescope, and it's going to scan the southern sky for 5+ years. And there are going to be millions of gravitationally lensed galaxies that are going to be detected with the Vera Rubin Observatory. And what it means is that that's big data. So we cannot use the traditional analysis methods we have been using on a handful of gravitational lens sources, because there are going to be so many more coming on in the future. So what we are doing is we are coming up with some novel techniques using machine learning. So machine learning is it's a recent technique that a lot of astronomers have been using to analyze this incredibly huge amounts of data from surveys like the Dark Energy Survey, the Vera Rubin Observatory. And what we are doing is we are actually training the machine by showing it a lot of data, and the machine learns the patterns from these data. So when you give it a new data set, it kinds of applies the patterns that it has learned to give us the desired output. And here I'm showing an example. So this is called supervised learning, where I'm going to show the machine lots and lots of images of strong lenses and not strong lenses. And the machine starts learning what a strong lens looks like. And then when you show it new data, and then the machine can now tell you if it's a strong lens or not. So there are a lot of techniques that, a lot of research that is going on into these machine learning techniques. That is currently what I'm working on at Fermi Lab, is to understand the dark energy and dark matter content using strong lenses and using machine learning algorithms with simulations and real data. So I'm going to end this talk by thanking the South Pole Telescope submillimeter Galaxies collaboration, who I worked with while I was at UIUC. And currently now I'm working with the Deep Skies Lab. It's a group of astronomers who are interested in machine learning applications. And I am working with Deep Skies at Fermi Lab. Yeah, I just want to end this image by showing our SP-DSFG collaboration photo from last year. So yeah, thank you.
Thank you so much. Thank you very much. That was wonderful. And I loved how you made a sometimes very complicated subject into something that we can understand. I do love the wine glass representation, and
yes,
that's why bending the light makes it just really, visible, easy to understand. So I want to encourage everybody to either put questions in the chat, or you can unmute yourself or raise your hand and we can kind of go through it. There is one question already regarding machine learning. Is there any cross-checking by astronomers to verify that the machines are accurate?
Okay, that's a really good question. So what we're doing in machine learning is actually we test how the machine is performing on unseen data. So we have a training data set, which we give the machine to learn. And then we have a separate test data set, which the machine hasn't seen, but we know what the true answers are for that test data. So once the machine trains on this training data, we now show it the test data set and measure the performance and see how accurate the machine has learned. So that's one way to check the accuracy of our machine learning model. And there are also a lot of citizen science projects which have turned into machine learning projects as well. So there is like Galaxy Zoo, where citizens have classified different types of galaxies, and that data set was used to train the machine and see how it's performing. So yeah, so we do have rigorous tests to see how the machine is actually performing.
That's great. I also loved the slides showing the same galaxy or Milky Way in the different wavelengths, and really what you can see is amazing, sort of seeing it side by side. One question I had, you had mentioned sort of earlier on about using gravitational lensing to study invisible dark matter, and I was a little unclear how that would work without any visible light.
Cool. Yeah. Let me go back. Yeah. So gravitational lensing. So the matter which is actually distorting the space-time, it's not just visible matter. It's the total matter in the foreground galaxy and around the foreground galaxy that is distorting the space-time. So when you observe a gravitational lens, and when you reconstruct with the lensed galaxy, the matter that is lensing is the total matter. It's both the visible matter plus the dark matter. So that's how you can estimate the dark matter content. So it's not just the visible light, which is lensing. It's also the non-visible light, which is lensing.
Awesome, that makes sense. And so it sounds like too, and you answered this during your talk. I was going to ask about the James Webb Telescope. Is the James Webb Telescope the first space-based telescope to use gravitational lensing, or was that done with Hubble as well?
No, Hubble has also seen gravitational. There have been optical images as well of these gravitational lenses. So this dark energy survey, which has observed gravitational lenses. There is Hubble Space Telescope, which has seen gravitational lenses. So James Webb is not the first. It's the first high resolution image in near infrared and mid infrared. So there was Spitzer before James Webb Space Telescope. That was not resolving these beautiful arc structures that you see. You would just see like a blob.
Mm-hmm.
Yeah.
That makes sense. Does anybody feel free to, oh, good. Okay, there's another. Otherwise, you'll just hear all my questions. What is this 70% negative pressure associated with the vacuum? I think he's talking about this.
Yeah.
Or she's talking about this slide.
Yeah, this slide. Yeah. So this is a current widely accepted theory of acceleration of the universe. It's called the cold lambda CDM model. And in this model, dark energy has negative pressure. I'm not entirely sure how I can explain the theory, but what the implication of this is that it causes the expansion of the universe. It's moving stuff away from each other, and instead of, like, for example, dark matter or any matter which has mass is bringing galaxies close to each other and causing these clumps, dark energy is moving them away from each other. So that's one of the consequences of this negative pressure. Sorry, I probably have not answered it very well, but that's the theory, currently widely accepted theory of cosmology.
It's amazing when you see it on the pie chart that way.
Mm-hmm.
How that is the most of it. Any other questions? We can, like I said, either put it in the chat or raise your hand or just unmute yourself as well. Well, we are just about on time. So, and again, given that Sreevani is 2 hours ahead, I'm sure she doesn't want to go too far over. So unless we have any other questions, we will then end it here. But I want to thank you again so much. Again, it was you did such a great job putting this very complicated theories and whatnot in a way that we can understand. And I want to thank you again for your time, and thank you to all of you for joining us, and hopefully we will see you all again soon. Oh, and
yeah, thank you so much for giving me this opportunity, and thank you for being here.
Thank you. Have a good night, everybody.
Good night. Bye.
Good night. Bye-bye.